Hi, today we're going to do number 199, binary tree right side view. So we're given the root of a binary tree, and we can look at this example, 1, 2, 3, 5, 4, and we want to pretend we're looking at it from the right side and read from top to bottom what values we see. So we see 1 first, 3, and 4, and that's what we get here. And now we look down here, this example 1, 3, 4, 5. So even though this doesn't have any leaves, we go here and get the 4 and 5 here. So we're going to have to traverse through this tree and find the rightmost value as we iterate through. So we can iterate through either using DFS or BFS. So DFS, there's two ways we can do it, using recursion or a stack. But kind of the same idea applies. So recursion, our base case, of it being null, we return up. And then what we're going to do before this is that we're going to have a result array, create res, to store the value. And we need a helper, and the key here is to take in the node and a depth, which is going to keep track of what depth we're in. And then here, if depth is the first one, if depth is equal to the length of res, which is the first one we see here, is going to be the rightmost. Push value to res, and we want to go down, call right side DFS, and then call left side DFS, and we just return res. So here, the time complexity is going to be O of n, because we're traversing through the entire tree, where n is the number of nodes in the tree. And then space complexity is going to be O of h, where h is the height of this tree. That's however long we store space of the call stack. So we can also do it recursively, I mean not with a stack. So when we do the same thing, we create res, but here we create stack and add the root and depth that starts off at 0. And here we do while the stack has a length, we pop it off, and here same thing. If depth is equal to res, we know it's the rightmost value, but the trick here is that we want to push, since the stack is last in first out, we want to push node.left first. If it exists, then node.right, and then we return res. And the time space complexity is going to be the same. And now the BFS way is that we create a queue. So we start off the same, we create a res to hold the values that we're going to return, and we can just return res at the end. And here we just add root to queue, and then we do a while, we loop through each level of queue, and then if it's the last one, if node is the last one, push it to res. And here you can just add push node left, then node right to it, and we'll get the same we'll get the answer. So here the time complexity is also going to be O of n, and the space complexity is going to be O of w, where w is the width, because the longest one is the width of it, which could be n divided by 2, which is O of n for worst case, or if it's just a straight line with like a linked list, it's just going to be O of 1 because it holds just one space at a time. So I would go with the recursive way because it looks the most cleanest, and we don't have to create this extra depth to keep track of. I mean, we do have to keep track of depth, but it looks like the most simplest solution. So we can go with that. And generally, O of H is preferred because you're just keeping track of what you're currently looking through rather than OW is what you might later get to. And I actually think like most trees will be more leaning towards more balanced than not. So, but I'll show you all 3 ways. So with the recursive way, we create a res, and then we return res. Now we create a helper function, DFS, takes in a node, and then a depth to keep track of what level we're at. And I like to call it so I don't forget. And we start off at 0. So our base case, if it's null, we just return. And then here, if it's the first one for that level, so if depth here is equal to res.length, and that's a trick we can use to see if it's the first one, we just push it, the value. So res.push node.val. And here, we want to go to the right side first, so DFS node.right, and depth we would just add 1, keep track of that one, and then we do the left side. Great, so now let's solve it with a stack. And a stack here, we're going to do the same idea, having a res to store the result. So we're going to handle the edge case if it doesn't exist, root, return res. And now we create a stack. And it'll have the node, which is the root, and it starts off as 0. And we can do this while the stack has a length. And then we pop it out, const. And we can destructure the value, so the node and then the depth equals stack.pop. Now we do a check if it's the first one. So if res.length is equal to depth, we push it. And now it's a stack. We want to do left side first. So only if it exists, because we don't have that base case if it's null here. Res.push, not res, stack. and then we do the right side. And now we have it, I believe. No, I forgot to, I knew I was missing something. First here, I forgot to add the def. Brackets. And there you go. And then the BFS way, we're still going to do the same idea where we start off with the res. But here, we create the queue. So const queue equals new queue. And then we push the root to it. And then here, we do a while loop while the queue is not empty. And we have to iterate through the entire level, so we get the size first. And then we do a for loop. And then here we want to push to the res if it's the last one, so I is equal to size minus 1. Res.push node.val. And here we can push the other nodes to the queue. So if node.left, queue.push node.left, if node.right, queue.push node.right. I forgot to pop off the current node. And there you go. So we can solve this problem using BFS or DFS. Using DFS, we have to keep track of the depth, and then we have to keep track of the first one we see it, we want to push it to the res. And there you go. And then while BFS, if you use a queue, is going to be the last one, as you can see here, it'll be the one on the right side. And because you push to the left first, and then you push to the right. And it's going to be your values you add to the res. And that's all. Thank you.